Hi guys, hi YouTube. Today I wanted to talk about how you draw cyclohexanes and turn a simple sugar molecule or a six-member ring into a cyclohexane and how to perform the chair flips for them. It's a pretty simple concept when you understand it, and I'll start off by showing an example of what a sugar molecule or a six-member hexane ring looks like and move on to a chair flip after that. So first off, what you want to be looking for is something like this. Excuse my terrible drawing, but it'll be a six-member ring, carbon ring. You'll have, well, it'll look something like this. Right, 6 carbons. This is a hexane, and this would be a cyclohexane. Cyclo meaning a cyclic molecule. Right. So we can add substituents to this. So let's add a methyl to every group aside from the sixth one. I like to normally number it like this, and you'll have a methyl for all of them. And of course, remember, you'll have another hydrogen coming out of here, and for all of them you'll have hydrogens, except for this one you have 2 hydrogens here as invisible hydrogens, and this will be your sixth molecule. Now for your hexane, or well, for your cyclohexane drawn as a chair flip or as a chair, drawing it as a line diagram for organic chemistry, you can draw it like this. You have your chair flips. So I normally like to label one of these as, this one as A, since it's tilted and facing towards the right. And then you could have another chair. This will be your other chair flip or chair diagram, which basically faces the left. Right? To draw these, it's very simple. You draw 2 lines. Let's actually show the right one. You draw 2 lines, and then 1 long line, 1 smaller line, and just do the opposite for this. You have a long line on this side, and you could do a short line there, or short line there, long here, and like that. It just needs to have 6 positions where you could add substituents. So let's draw out these substituents as hydrogen first, and then I'll draw them out as methyls, and however you really want to draw this molecule. It becomes pretty simple after you do it a few times. So your substituents always start off as this being axial, right, facing upward, axial, and this way being equatorial. Axial meaning positioned in an axial view, and equatorial meaning facing outward, right? And basically you'd alternate throughout the molecule. So this one's going to be axial now, facing downward, and you have an equatorial facing upward. Here you're going to have an upward axial and an equatorial facing outward. On the 4th carbon, you have an axial facing down and an equatorial facing up. Then on the 5th carbon, you'll have an axial facing up, equatorial facing down, and same for the 6th one. You'll have an axial facing down and an equatorial coming out. Now, for all of these, you could draw hydrogens at the moment to just show a simple depiction of what one of these chair diagrams would look like. And the same thing happens here on the B diagram, but something odd, or there's a simple trick to flipping these, right? So let's number these as 1, 2, 3, 4, 5, 6. On a B-shaped chair flip, your carbon 1 basically shifts over to carbon 2. So you'll have 1 over here 2 over here, 3, 4, 5, 6. So anything which was on axial over here will, well, axial facing up will be on equatorial facing up over here. So let's again draw these out. Give me 1 second. Right. Now you'll have hydrogen, 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 hydrogen. This is a simple drawing for it. We'll go into more details about it in a second once I'm done drawing this. So these will be your 2 chair diagrams. Now, when we're drawing this, when we're drawing something like this here, which has substituents, let's actually add a little more. Let's add an ethyl group there, and let's say a phenyl group here, right? Or a tributyl. Let's actually do a tributyl because it'll explain it'll explain a more complex topic when we're doing that. So let's erase the hydrogens on here. You always want to draw the skeleton when working through a test. Eraser. Okay, so you always want to draw a skeleton like this when doing a test, just because it'll make your life much easier to visualize it. I normally like to still draw my hydrogens because, I mean, you really don't want to get confused on a test, and you want to double check everything in this kind of case. So I found it best being able to just draw these out. Anyways, let's get into drawing this molecule. So one, let's say these are drawn like this. Let's put this facing into the paper. This would be a perspective drawing. Let's put the terbutyl facing outward out of the paper, and let's draw this methyl coming out of the paper. Cool. So on group 1, we want to put whatever is facing out of the paper on the upward position. So this here is upward, and the equatorial position is downward. Same. Let's take an example of the second carbon. The axial would be facing downward. The equatorial is facing upward. So it's nothing really related with the axial and equatorial. It's just about which way the methyl group is facing, right? So in carbon 1, you have a methyl group facing outward. So it'd be like this, and an invisible hydrogen coming out like that. For carbon 2, you have an ethyl group coming out. So you have CH2, CH3, like that there. And then a hydrogen facing down on an axial position. So, yeah, on axial over here, you'd have it facing down. Let's quickly draw this back. I don't know why I erased. So on carbon 3, you'll have a downward facing, or into the paper, facing methyl. So we could draw that as this. And here you draw an H, a hydrogen facing on the axial position upward. On the 4th carbon, you'll have a tributyl group facing out. So you can draw that like this, a terbutyl, and you'll have a hydrogen facing down on axial. The terbutyl is on equatorial. Then on carbon 5, you'll have a downward facing CH3 and an upward facing invisible hydrogen. And here you'll just have both hydrogens, right? Now let's do the chair flip version of this. And that would be done very, very simply. CH3 on this carbon, or on A flip, on the A chair config will have CH3 up. So you also want CH3 up on this one. This one would be equatorial now. Your hydrogen's on axial. Similarly, we'll do all of them just like that. Carbon 2, you have on axial now. Well, the ethyl you'll have on axial, and on equatorial, and on axial, yeah, and then on equatorial you have a hydrogen. Carbon 3, you'll have CH3 facing down and H facing up. Carbon 4, you'll have a terbutyl now on an axial position and hydrogen on equatorial. And then on carbon 5, you'll have CH3 on axial, equatorial being hydrogen, hydrogen, hydrogen on carbon 6. Now, let's talk about the important concept I was talking about initially. You want to determine which groups are bulky and which groups are not. So your CH2CH3 is bulky, your terbutyl is bulky, and normally you don't want to put them on an axial position because it'll lead to 1,3 diaxial strain, right? You'll cause strain between the hydrogen bonds and the terbutyl, and you don't want to do that because molecules don't like having strain. They'll be high in energy and unstable. So the most stable conformation would actually be your A molecule or chair flip, because both of the bulky groups are on equatorial positions, not causing that kind of strain. So it's lower energy, more stable, whereas your B conformation has the highest energy groups on axial positions. There'll be a lot of strain on the molecule, making this less stable of a conformation, and this more stable. Happening on carbon 1 and carbon 3, you'll have strain. You'll have diaxial strain. On an equatorial position, you don't have that kind of strain. So this is an introduction to drawing cyclohexanes into chair flips. Thank you for tuning into this video. Please subscribe. Thank you.